Okay, good evening, everyone. So let's get started. So by yesterday, we finished the chapter 2, that is solution to system of nonlinear equations. So today we're going to start the next chapter, that is basics of the finite difference method. Okay, also known as FDM. So we're going to start the third chapter, that is basics of the finite difference method. Now, you can think of this chapter as a kind of a bridge chapter because it is going to bridge the first two chapters that we have, in which we have learned solution to a system of linear equations and solution to system of nonlinear equations. Okay, to essentially to the solution of ordinary differential equations and solution of partial differential equations. Okay, so essentially this is going to help you convert or solve some of the problems that you would get. I mean, essentially all the problems that you would get from the solution of ODEs and PDEs, which are the next chapters that are going to come, to kind of cast them into the system of linear equations and system of nonlinear equations. Okay, so essentially what happens is that all the physical phenomena that you would observe or that you use in science and engineering, these are all expressed in terms of differential equations, right? These are in terms of differential equations. Whether you take heat transfer, fluid flow, or bending of a beam, or diffusion in a solid, or chemical reactions, all these things, these are all basically differential equations. They can be essentially ordinary differential equations, or they can be categorized as partial differential equations. Okay, so but then we're going to but then you cannot or we cannot solve these ODEs and PDEs. ODEs to some extent we can solve, but the PDEs we cannot solve analytically, right? Analytically, or even ODEs, it is very difficult to solve for several problems. So we cannot solve analytically, so won't be able to solve analytically these equations, these ODEs and PDEs. Okay, except for very simple situations. That means very simple problems, and then for very simple boundary conditions, for simple boundary conditions and so on. Only for certain of these instances we can solve these ODEs and PDEs analytically. For everything else, we need to resort to numerical methods. That means we can only solve them numerically. I think that explains why we have so many simulation software around, like ANSYS or OpenFOAM or any of the structural solvers, Abacus, and so on, because these are all solving your partial differential equations, the governing partial differential equations and ODEs using some numerical methods, right? You're only getting a numerical solution, not an analytical solution. Okay, so that means we should kind of keep in mind that when we solve these equations, what we are trying to do is that we are going to convert these ODEs and PDEs into, which are basically the governing differential equations, right, into a set of linear or non-linear algebraic equations, right? So we kind of distinguish between what are partial differential equations and ordinary differential equations and algebraic equations. Okay, so we are going to convert all of them into algebraic equations, whether they are going to be linear systems or nonlinear systems. We're going to convert them. Now when we make this conversion and when we try to solve, we are making approximations. Or we can also say that we are introducing or incurring errors at each phase, right? That means we're going to make introduce errors in terms of identifying the domain, right? In terms of applying the boundary conditions, and in terms of converting the partial differential equations into algebraic equations, right? And eventually, in the solution of algebraic equations also, as we are going to use computers which have only a finite precision. So we are only going to not only introduce errors, the solution we get is not exact. The solution we get will be only approximate in nature, because we are incurring all these errors, and also we are using finite precision computers to solve for this algebraic equation. Okay, that's what we should keep in mind. Now, going forward, we should have a means of quantifying these errors, okay, that are introduced in the solution procedure. Okay, these errors that are introduced in the solution procedure. Okay, so we should have a means of quantifying these errors. So we're going to look at how to quantify these errors, or how to kind of identify them, and then we should also know whether these errors are increasing or decreasing from iteration to iteration, from iteration to iteration, or from time step to time step. That means if we have some unsteady problem from time step to next time step, we should know whether these errors are actually increasing or decreasing, so that we can comment upon whether our solution is going to converge or not, right? So then we can comment on whether our solution is going to converge or not. Okay, so that's what we will be able to comment on. Okay, so let us look at some sources of error. So the sources of error and their nomenclature, how do we define them? So we said essentially you have a set of governing differential equations. Okay, so you have a set of governing differential equations which are essentially here. Now these governing differential equations are then applied. We apply a procedure called discretization. Okay, by discretization, what we mean is that we are going to convert these governing differential equations into set of algebraic equations, right? We are converting these PDEs and ODEs into a set of algebraic equations. Algebraic equations are in terms of some U, V, W, temperature, pressure, whatever, whatever you have times the coefficients, right? You have some AX equal to B is what you're going to convert them into, right? Instead of these from these governing differential equations. So for that, we make use of several methods. We can make use of several methods. Those methods are known as there are several methods to do the discretization. These are known as the finite difference methods, or you have finite volume methods, or you have finite element methods. Okay, if you're using solid, solid mechanics, more finite element is much more used. And then you also have other methods such as the spectral methods. Okay, and you have some methods that are known as the pseudo spectral methods. And then many other types are available. Okay, several other types of methods are available, using which you're going to essentially convert all these, essentially going to apply discretization, okay, and then convert the governing differential equations into set of system of either linear or nonlinear algebraic equations. Okay, most likely you're going to convert them into set of linear algebraic equations. So that's what you're going to convert. So that's what you're going to convert them. And then, of course, we have already seen how to solve these systems, right? We have already seen either you can use LU decomposition or Gaussian elimination or try a TDMA, all sorts of things to solve for linear systems. And then if it is nonlinear, we have just looked at yesterday. If it is just a single equation, we can make use of either bisection method, Newton's method, or secant method. Or if it is a system of equations, we said the Newton's method was readily applied, right, to system of nonlinear equations and so on, right? So in all these methods can be applied. Now, we are looking at this particular thing, that is discretization in this particular chapter, which forms the basics of the finite difference method. So we're going to essentially look at this method, that is the finite difference method, okay, because that is something that is very easy to work with, and then it is of very much academic interest. Okay, so depending on that, the other methods can be built up later depending on your interest. Okay, fine. What kind of so we have, as I said, there are several sources of error. We define several types of errors. The first one is we want to know how well the solution of the algebraic equations approximates the governing partial differential equations. Okay. How well this solution of the algebraic equations approximates the governing partial differential equation. So we call this particular error as the truncation error. Truncation error. Okay, we represent it using TE. Now let us look at the partial differential equation. Let's say I'm able to write some function f of, let us say, if phi is my variable. I have, so my partial differential equation or ordinary differential equation is going to consist of several variables. And essentially, let us say my governing differential variable is phi, and then it is going to consist of several derivatives of this, right, in a partial sense. So it could have derivatives of phi with respect to x. It may also have derivatives of phi with respect to y. It may also have second derivatives, right, in x square and in y square. It may also have derivatives with respect to time and so on, right? So it could be essentially my partial differential equation is made up of some function of phi partial x, partial phi partial y, partial square phi by partial y square, and so on, all these things. Now, if I'm able to solve this function analytically, then I'm going to obtain some solution phi, which is a function of x, y. Let us say if I'm looking at two-dimensional space, if it is three-dimensional, it will be x, y, z. And then if it is unsteady, I'm going to get some phi of x, y, t. Okay, now here we realize that x, y, t, so phi is a continuous function. That means I can substitute for any value of x, y, and t into this, and then I'm going to get the value of phi, right? That is what we have. But on the other hand, if you look at the corresponding algebraic equation, then what we have is, so if we have converted all these things into a set of algebraic equations, then we may end up with some function capital F. This could be either linear or nonlinear depending on the case, but then it's a function of some capital phi. Okay, when I say little phi here, like we can also say capital phi equal to 0. So this is basically some function capital F bar of some phi, okay, equal to 0. Again, phi is a function of space and time. So now this phi is the solution to the set of algebraic equations, right? We are able to solve this algebraic equation using some Gaussian elimination or LU decomposition or something like that. Then the phi is obtained. Phi is a vector of all the unknowns. But then we know that because this is only a discrete equations, the solution of phi is only available at discrete points, that is xi, yi, and discrete times ti, right? So I have only a solution at specified x and y locations and ti, right? I don't have solution at in between different xi values, but then if I want, I should be able to somehow interpolate and calculate that. Okay. So now we know that essentially now if I'm going to substitute for this phi into this equation, it is going to solve. So the analytical solution, that is phi, right? Phi is the analytical solution, satisfies the governing partial differential equation exactly, right? It satisfies exactly because that is how we have solved. Now, similarly, the approximate solution, that is the discrete solution, which I have denoted using capital phi, is going to satisfy the algebraic equation, that is f equal to 0. It's going to satisfy this algebraic equations exactly, right? However, this analytical solution, right, is not going to satisfy the algebraic equations I have. So the analytical solution is not going to satisfy the linearized or even otherwise the linearized algebraic equations, right? We know that it is not going to satisfy this thing because this is obtained by solving the partial differential equations, whereas capital phi was obtained by solving the set of algebraic equations. So as a result, what we have is, as a result, the amount by which, the analytical solution fails to satisfy the algebraic equations is known as the truncation error. Okay, that is known as the truncation. That means the amount by which the algebraic equation, so the exact analytical solution fails to satisfy the algebraic equation. That means f of little phi is not equal to 0, right? And this exactly this amount is known as the truncation error TE. That means f of phi in some norm is known as the truncation error. Okay, that means if I know the exact analytical solution, I can just substitute for that into the linear algebraic set, and then that is going to give me what is the truncation error that has taken place. Now, this is the truncation error for the entire equation as such. This is for the entire equation. We're going to see a slightly different definition when we apply it to calculating a particular derivative. Okay, that is going to come up in a little while. So then we're going to see a slightly different definition for the truncation error. Okay, so that is how you calculate the truncation error. But then, of course, we realize that to calculate truncation error, we need to know what is the exact analytical solution to the problem, which may or may not be available in all instances, right? If it is a simple problem, we know that we can quantify that by substituting it into the converted algebraic equations. Otherwise, we won't be able to actually calculate truncation error a priori for the entire system. Okay, so but then we'll be able to calculate truncation error by different means, by looking at different truncation errors of different derivatives that are there as part of these equations and so on. So that's we're going to see that little later. Okay, now before we go ahead and solve for the solve or obtain these set of algebraic equations, as I mentioned, we have to perform this to obtain algebraic equations. We have to perform this operation that is known as the discretization, right? That means we are going to essentially convert our, so discretization can mean two things. One is the conversion of PDEs into algebraic equations. Then it can also mean converting or your domain, okay, whatever is the region of interest, into finite regions, okay, or also known as mesh generation. I think you're probably more familiar with the word mesh generation. So that means, as we know, we have to essentially come up with some kind of we have to identify several points in space, or essentially volumes in space, depending on the method we would use. Let us say if you use finite difference method or finite volume method, we're going to essentially discretize our domain into finite volumes or finite elements or finite points and so on. Okay, finite vertices and so on. So we are going to use one of these methods. So essentially now we have to essentially generate or mesh generation. What it means is that we need to generate a set of points that are connected to each other in a certain way. Okay. So what do we call? So that kind of meshes, we kind of say that if these meshes are connected in certain way, we call them that particular mesh as a structured mesh. You might have also heard the name unstructured mesh. Okay. So if the points are, for example, we can, if I draw something, you would be easily to say what is a structured mesh, what is an unstructured mesh. So I have an example of something here in black, and then you have probably also have seen some kind of a triangular mesh, which is going to be like that. Let us say this is an unstructured mesh. Okay, so we have some unstructured mesh like this. Okay, so this is a structured mesh example. This is an unstructured mesh example. So I mean, what is the underlying difference? Essentially, if every node in the interior of the domain or interior of the mesh has the same number of neighbors all around, if it has the same number of neighboring nodes, just 1 second, same number of neighboring nodes, then we call this as a structured mesh. That means wherever you go, this particular node has only 4 nodes, right? It has only 4 neighbors. Similarly, if you go here, it has only 4 neighbors and so on. So such kind of very structured arrangement, we call it as structured mesh. Whereas if you take certain meshes, they may, like for example, this triangular mesh, this particular mesh has, let us say, if you pick any vertex here, this vertex may have more number of nodes here than compared to another vertex here. This basically depends on how many triangles are sharing this angle, right? So as a result, this kind of when the number of nodes differ from vertex to vertex, okay, number of neighboring nodes differ from vertex to vertex, then we call it as an unstructured mesh. Okay, we call this as an unstructured mesh. Fine. So in general, typically your finite difference methods are typically applied to structured meshes. Okay, they are not very much applied to unstructured meshes, whereas your finite volume methods and finite element methods, typically they are applied to unstructured meshes. However, there is nothing that stops them from applying it to structured meshes. Okay, so but then preferably you would like to use finite volume methods and finite element methods on unstructured meshes, because that is where their stronghold is. That is where their applicability comes into picture, or their use comes into picture. So that's why typically finite volume and finite methods are applied on unstructured meshes. Then you have these other methods, which are the spectral and the pseudo-spectral methods. So these methods are typically applied on some special points. Some special points depending on the corresponding polynomials that are used. And these are called collocation points. Okay. So the underlying polynomials define where you should place these grid points. Okay. However, these spectral and pseudo-spectral methods are very powerful in terms of they have like very high accuracy. So, however, they cannot be applied to solve solutions in complex geometries. That is the problem, but they have really very high accuracy compared to all other methods. Okay. So that's about essentially applying, how different methods are applied to convert our existing partial differential equations into algebraic equations. Okay, any questions so far, anybody? either from here or from the previous lectures. Any questions?
Clear, sir.
Sorry?
Yeah, it's clear, sir. Yeah.
It's okay, fine. Shall we proceed? All right. Okay. Then let us look at the other types of errors. The other error we have is called as the discretization error. Discretization error. So this error is basically the difference between the exact analytical solution and the numerical solution that is obtained on a computer with infinite precision. Okay, that means that means discretization error is going to be, we have phi, that is the exact analytical solution, and then we have capital phi. Okay, obtained on an infinite precision computer. That means this is something that we don't have access to, right? Because all the computers we have are finite precision computers. But then this difference between the exact solution and the um, uh, numerical solution, capital phi, obtained on an infinite precision computer, we call this as the discretization error. Unlike the truncation error, the discretization error also takes into account the errors and approximations made in the boundary conditions. Okay, so the discretization error also considers the errors that are there in the boundary conditions as well of the problem. Okay, unlike the truncation error, which is going to only look at the governing differential equation, not the boundary conditions as such. Okay, so that is the discretization error. Similarly, we can also define a final another error that is known as the round-off error. Okay, the round-off error, as we know, all the calculations on a computer are going to suffer from round-offs, because as we have seen in the couple of example problems, we always have some kind of rounding that happens. If not at the 4th digit, it may be at the 5th digit, or maybe at the 16th digit or something like that. So all the computers have to round them off, all these things. I know the way the floating point numbers are represented. So as a result, the difference between the numerical solution obtained on a finite precision computer and an infinite precision computer is known as round-off error. That means if I were to define round-off error, it's going to be some norm between capital phi of the finite precision computer. That means whatever we solve on our computer versus whatever it would be if you are solving on it on a infinite precision computer. Okay, that is known as the round-off error. This is some norm. Okay, essentially round-off error is responsible for essentially making making even theoretically stable algorithms to diverge, right? For example, we have seen in the Gaussian elimination and in other aspects, other algorithms, that depending on how you choose the pivoting and other things, the Gaussian elimination can actually diverge and give you some other answer, right? This is because of the accumulation of round-off errors. So although Gaussian elimination is kind of stable, it is going to be, it's supposed to give an answer, but then because of round of errors, this actually can give you incorrect answers. Okay. So we need to be very careful with this round of errors, because it may make our solution to diverge as we progress. Okay. So that's about the round of errors and the truncation error and the discretization error. These are the main three types of errors that you would get. Then let us also look at something that is known as what is known as consistency, stability, and convergence. Okay. So what is consistency? So consistency or consistent scheme, we mean by consistent scheme, yes. So we define this truncation error, right? So the truncation error should become smaller and smaller as the mesh and the time step are made smaller. That means, let us say for your domain, you have taken some grid spacing. Okay, let us denote this using delta x, delta y. You might have also taken some time step, right? If you want to calculate an unsteady phenomena, you have taken some time step. Now, as you make these smaller, that means as these goes to zero, you make them as smaller and smaller. Then the truncation error that you have should go to zero. That means in a limit, you should be able to get smaller and smaller errors, right? Only then we say that the particular scheme we have applied is consistent scheme. Okay, then only we can say that particular scheme is a consistent scheme because it is behaving in a consistent manner, right? If it is not going to behave in a consistent manner, for example, if you have taken, let us say, cells of size 2 millimeters, okay, in a big problem, then you are getting some answer. But then when you take delta x equals 5 millimeters, you are actually getting a better answer. So now this means that your scheme that you have used to discretize your equations is not behaving in a consistent way. It is supposed to behave. It is supposed to give you better answer as at 2 millimeters rather than at 5 millimeters. Okay, so that means there is something else at play, which is basically making the truncation error to give you better results when you have coarser meshes. That is the thing. So now, well, can this happen on using some discretization schemes? Yes, it can happen. We'll probably look at some schemes like that which are not consistent, okay, later on in the course. But then we have to be always careful what kind of schemes we are applying, and we should always check for that they are consistent. Okay, we don't want to work with inconsistent schemes because they are not going to give you results in a reliable way, because the finer the mesh you make, the smaller the time step you make, you are actually going to deviate from the correct results. You're going to get incorrect results as you go with them. Okay, so that is known as consistency. Then let us look at something that is known as stability. Okay, stability is usually applied for unsteady problems. Okay, also known as time marching problems. It is also applied to essentially to problems where there are iterative solutions are there. We're going to apply the stability concept. So what stability means is that the errors, whether they are round-off errors or other errors, are the errors are not going to grow from time step to time step or from iteration to iteration. Okay, the errors are not going to grow. That means the errors either will stay the same or decrease. Okay, then only we can say that the particular scheme is stable. If the errors are going to grow, right, if they're going to grow, then we call that scheme as unstable, and we won't be able to unfortunately use it because the round-off errors will grow, and then they're going to contaminate the solution. Eventually we're going to get all very big numbers, which are not useful anyway. Okay, so that's about stability. We are also going to look at some schemes and how to evaluate whether they are stable or not later on in the course in this particular chapter in the basics of finite difference method. Okay, then we have something that is known as consistency, stability, and convergence. So convergence, we can say that a scheme that is both stable and consistent is a convergent scheme. Okay, that means we say that if it satisfies the particular scheme we are using, it would satisfy both stability and consistency properties, then we can call that scheme as convergent scheme. Of course, we want to work with convergent schemes. There is also another context in which convergence is used. We also say convergence to a mesh independent solution. So what we mean by this is, many a times we would not know whether there is an exact analytical solution, whether there is a correct answer to a problem that we are solving. Let us say if you are working in a complex geometry, let us say you're trying to calculate what is the heat distribution in a battery cells, or if you're trying to calculate what is the heat load, thermal load on a brake drum, or or on the brake brake element or something like that, then in all those cases you will not have an exact solution. So you have to rely on some kind of mesh. Okay, so what you say is that you find a solution, you find essentially the temperature distribution over the entire brake, let us say using some r theta phi. You have obtained this on a domain of maybe, let us say, 15 million cells, 50 million cells. Then you would also run again the same problem on, let us say, using maybe 80 million cells. This is a much higher number. So, and then you show that at those cells which are there in both of them, this temperature profiles are not very different. They're all, essentially they are matching with each other between these two. Then we can say that if both are matching, then we can say that, okay, we have reached a grid independent solution. That is also known as, we can say, a convergence. The solution has converged to something like this. Okay, that is also typically used in this context. Okay, so that's about essentially the introduction to the basics of finite difference method, in which we looked at the truncation error, discretization error, and the round-off error. And we also looked at how different methods are applied to convert the governing partial differential equations into a set of algebraic equations. And then we looked at what is meant by consistency, stability, and convergence. Okay. Now let us look at, let us get into discretization or calculation of a derivative using finite difference methods. Okay, that means we're going to numerically evaluate a derivative using finite difference method. Okay, so as you recall, we may essentially, let us say if you have a one-dimensional problem, you may kind of discretize it with several nodes like this. Typically, we'll have some dependent variable in a partial differential equation. The dependent variable, let us say if it is u or f, and the independent variable is something like x or y. Okay, the independent variables are x or y. That means we have to typically calculate what is the change of u with respect to x or change of u with respect to y. Okay, that is, these are there in the governing partial differential equations. As a result, we have to write an approximation for these dou u dou x and dou u dou y. Okay, that means the first step is basically in the x direction, we're going to discretize with several points. That means we have done mesh generation. Let us say these points are I minus 1, I plus 1, I plus 2, I plus 3, something like that. These are all the x values. That means I can write, when I say x sub I minus 1, I'm referring to the x coordinate of this point. Similarly, let us say for these points, we also have the u values. Let us say the u values are known. So this is going to be ui minus 1, this is ui, this is ui plus 1, this is ui plus 2, and this is ui plus 3. Okay, so that means we know how is this function, varying. So we know, let us say it is varying something like that. So we know the values of the function. But then now we have to calculate what is partial u, partial x. Again, because we are working with a discrete set of points, we cannot evaluate dou u dou x at wherever we wish. but we can only evaluate at certain points. Let us say at I minus 1, I plus 1, all these points only we can evaluate the derivative value. Okay. So to do that, we are going to essentially make use of certain approximations. Okay. But then we also realize that now this derivative at I can be either expressed using this value, that is ui, and also in at ui plus 1, or this can also be expressed in terms of this value and this value, or this can also be expressed in terms of this value, and this value, and so on, right? There are essentially several things that we can do. Either I can go in the I plus 1 direction and calculate the derivative, or I can go I minus 1 direction and calculate the derivative, or I can use in a symmetric way by making use of both I minus 1 and I plus 1 values. So if you go in the I plus 1 direction, these kind of derivatives are known as forward differences or forward differencing. If you go I minus 1, I minus 2, all these points, if you make use of those points, we're going to call this as backward differencing. And if you're going to make use of I plus or minus 1 for calculating value at I, then this is known as the central differencing. Okay. Now, okay, while these exist, we may be making use of them. They may be necessary in certain instances. For example, let me draw a two-dimensional grid here. Let us say we have a domain like this, and then we have discretized it with several points like that. So let us say we have 1, 2, 3, something like that. This is, let's say my mesh is something like this. Okay. So I have some mesh here. Okay. And then I have mesh point. I have meshed it in the y direction also. Okay. So this is also in the y direction. Okay. Now, essentially what we have is we have both x and y. Let us say this is the x direction, this is the y direction. Then any point I can think of it like I comma j, right? I can think of I comma j. If I go in this direction, it's going to be I plus 1, I plus 2, and so on. If I go in this direction, it's going to be I minus 1, and so on. If I go in this direction, it's going to be j plus 1, and so on, and then j minus 1 if I go like this. Okay. But then as long as we are in the interior of the domain, that means anywhere here, we can make use of the central differencing operators, because you have 4 neighbors. You have if you are a point I, you have I minus 1, I plus 1, j plus 1, and j minus 1. So interior points, that means central differencing, if I were to call it as CD, can be used for interior points, because you have availability of the values of u at the neighboring points in all directions. But let us say if you want to calculate a derivative for let us say you want to calculate the derivative for a point on for a point here, then the only data you have, let us say if this was I, right, the only data you have is I plus 1, I plus 2. You can only go in this direction because there is nothing that exists in the left direction. So as a result, you cannot use this thing. So at this boundary, if you want to calculate, or even at interior points, you have only data available in one direction. For example, here I can only make use of forward differencing to calculate derivatives here. Similarly, if I am here, I can only make use of I minus 1, I minus 2, and so on. So that means I can only make use of backward differencing. Similarly, I can also make use of forward differencing if I am on this thing, and if I am on the top, I can only make use of backward differencing. But if I'm on the interior, I can essentially make use of central differencing. Okay, that means we can only make use of forward differencing here, backward differencing here, and so on. So that is how we decide what difference to use where, and that is how these have come up. Okay. Now, what do? The first step in doing this thing is to make use of the Taylor series expansion. Okay. That means, let us say we have made our mesh, and this mesh has a width of delta x in the x direction. Okay, and then has a width of delta y in the y direction. So we have these two. First, let me look at essentially one-dimensional problem. So we have only delta x is the grid spacing. Let me consider uniform meshes for the ease of calculations. Let us say uniform meshes. When we say uniform meshes, we have xi minus 1 equals xi plus 1 minus xi equals xi plus 2 minus xi plus 1. All these things uh, xi plus 1. All these things are equal to delta x, which is the same, right? You basically have a uniform mesh, which I would like to also represent using little h. Okay, this is also the grid spacing because it will be easy for me to write. Okay, so I may interchangeably use delta x and h. Then I can also denote what is my u value at I plus 1, right, as u of I plus 1. I can also write this as essentially u of um, x plus delta x, right? If my u of I has a value of u of x, this is u of x plus delta x. Okay, that's what I'm trying to write. That means I can express ui plus 1 about ui. Okay, so I want to write ui plus 1, which I'm kind of writing in a slightly different way. Instead of using this parenthesis, I'm writing ui plus 1 equals u sub I plus 1 equals ui plus, using Taylor series expansion, I can reconstruct what is u at I plus 1 as delta x times partial u partial x at I plus delta x square by 2 factorial times partial square u by partial x square at I plus delta x cube by 3 factorial partial cube x by partial x cube at I plus and so on, right? I can write like this. Of course, as I have said, I can make use of, instead of delta x, I can also write h. Okay. But then let us say I'm interested in calculating what is partial u partial x at I. Okay. Then I can, of course, bring this guy to the left hand side. I can write for partial u partial x I is going to be ui plus 1 minus ui, right, times delta x is there. So ui plus 1 minus ui minus delta x square by 2 factorial dou square u by dou x square at I plus order delta x cube and so on, right? So many terms. But then I want to calculate numerically a value for dou u dou x. So this is going to be partial u partial x at I equals, I'm dividing the delta x to the right hand side. So it's going to be ui plus 1 minus ui divided by delta x minus this delta x square by 2 factorial divided by delta x is going to basically make it delta x by 2 dou square u by dou x square at I. Okay, and so on. Now, because I want to calculate partial u partial x at I, and I know the values of ui and u plus 1 and then delta x, I want to approximate this dou u dou x at I approximated as ui plus 1 minus ui by delta x. Okay. In doing so, I am essentially truncating the rest of the series, right? We're essentially truncating the series. So we can also call this, for this derivative, as this is the truncation error. Okay, so this is the truncation error. And we know that the truncation error for this particular derivative is of the order of delta x. That means the leading error term that we are truncating, which we are not representing, is of the order of delta x. That means delta x to the power 1. So as a result, this particular scheme, which is dou u dou x at I equals ui plus 1 minus ui by delta x, is known as a first order accurate scheme. Meaning if I'm going to make my mesh instead of delta x, if I'm going to make half of the delta x, the truncation error that I had before is only going to become truncation error by 2 because the truncation error goes as order delta x, it is only going to become half of it, right? So that is a consequence of a first order accurate scheme. Okay. Now, of course, first order accurate schemes are two cores. Okay, because the error is large. And are two cores to be used in general, okay, in any calculation. So as a result, we will resort to somewhat higher order, something like a second order accurate schemes, or even third order accurate schemes in the calculation of the derivatives and so on. So we have to come up with a particular method. So in this case, essentially, it was very simple because we have the Taylor series expansion, and then we could find what is dou u dou x by simply sending the things to the left hand side. But it is not. We need to come up with a particular method in which we can derive an expression. We can derive an expression for any given derivative, for calculating derivative to the accuracy that is desired. To the desired accuracy. Okay, so we need to come up with a particular way of doing this thing so that we can always express what is the derivative, whatever derivative we want in terms of the neighboring values of the function values. Okay, ui plus 1 and so on. Okay, so that is going to be the essentially is what going to come next. So we are going to look at that. Before that, any questions? I think we just finished the time, so I'm going to stop here. But then please ask me if you have any questions, either from today's lecture or from previous lectures. So going forward in tomorrow's lecture, we're going to look at how to obtain expressions for these derivatives to whatever order of accuracy we intend to for using forward differencing, backward differencing, and central differencing schemes. Okay, so that is what we're going to do in tomorrow's class, and then move forward to calculation of truncation error for certain equations. Okay, so that is what is going to come next. Okay. Then I'm going to stop here. Any questions, anybody?
Sir, may I know like what will be the syllabus for the exam? Like,
The exam is only on November, right? In November, isn't it?
I believe it is on 26th October.
Oh, 26th of October, is it?
Yes, sir. I would, yeah. That's
Yeah,
my
okay.
understanding.
We'll decide. I think most likely we'll keep it maybe depending on how much we cover. I mean, we'll definitely have first chapter and second chapter, that is system, solutions to system of linear equations and nonlinear equations. Depending on how much we cover, we can also keep the basics of finite difference method. Okay.
Okay,
Yeah.
sure, sir. And one more question is like, means on the questions type for the exams, will it be a problematic or will it be a derivation?
It will be a mix of both. There may be some derivation, some small derivation, and then there will be numerical, calculations.
Okay, sir. Okay, sure.
Yeah, both will
Thank
be there.
you.
Depending on, I'll probably see. Maybe we'll have a 1 hour or 1 hour 15 minutes exam or something like that for the midterm, and depending on the syllabus, we will decide. Okay, in terms of how much we cover. First
Sure,
two
sir.
chapters are definitely there, and then third chapter we'll see whether we need to include or not.
Okay, okay, sir. Sure.
Yeah.
Thank you, sir. Thank you.
Thank you. Okay, if there are no more questions, then I'm going to stop here. I'll see you guys tomorrow at 4 o'clock. Okay.
Thank you, sir.
All right. Thank you. Thank you,
Thank you,
everybody. Thank you.
Thank you, sir.
Thank you.
Thank you. See you tomorrow.